Testing, testing. Okay, we've got some more questions to go through. These questions were given to me today on the 18th of March. And there's some more questions on this chapter. Everyone seems to dislike the sum and products of roots. I was given question 5 again, but since I've done that in a previous video on the 13th, I'm going to skip that one. I can move to a couple of the harder ones. So, so for question 7, so do that one first. All right, so we can see down here, the roots of the equation x squared minus 6x plus 7 equals 0 are alpha and beta. So remember, sum of the roots is minus b on a, so it'll be 6 on 1, which is just 6. And the product is c on a, which is alpha times beta, equals 7. Now, with those two, you somehow have to come up with what these are here. So, so basically, let's find out what these are. So if these are the roots, now, and beta plus alpha are roots. So let's find the sum of these new roots. Sum would be alpha plus beta plus 1 on alpha plus 1 on beta. Oops, I wrote that again. Okay, getting messy. Maybe I'll switch to my pencil. I should do that. Wait me a moment. There we go, let's make it nice and sharp. All right, so the sum, now this part here, I already know what that is, that's 6. So why don't we just write that? 6. Okay, as for the rest, well, you can't reduce that. But what if I was to do something like this? I'm going to write them with a common denominator. How do I do that? Well, a bit like when you're working with numeric fractions instead of algebraic fractions, you can multiply top and bottom of both by the other denominator. So then that was beta, so then alpha times alpha, alpha, alpha. And then they'll both have a denominator of alpha beta. Oops, alpha beta. And then alpha plus beta or beta plus alpha, doesn't really matter. Okay, so I know what that is. So I've got my 6 plus, I've got 6 on the top, 7 on the bottom. And then that can be reduced. 6 can be reduced, 6 wholes can be 42 on 7 plus 6 on 7 is 48 on 7, which isn't quite 49 on 7. Unfortunately, there's not much you can do about that. Okay, so now the product of roots. All right, alpha plus 1 on beta times beta plus 1 on alpha equals alpha times beta plus, now we fully expand that. Okay, we'll have 1 on alpha plus beta on beta plus 1 on, if you multiply the last two, 1 on beta times 1 on alpha is 1 on alpha beta, like that. Okay, which would be, now alpha times beta is 7, plus alpha and alpha is 1, they cancel, plus beta and beta is 1, they cancel, plus 1 over that, so that's 1/7. So we have 9 plus 1/7 as an improper fraction. 9 wholes, 9 times 7 is 63, so 63 on 7 plus 1 is 64 on 7. Okay. Now we have to find a quadratic with those roots. So remember, x squared minus the sum of the roots, x plus product. So thereby, x squared minus 48 on 7, x plus 64 on 7. And because we're finding a, it doesn't really matter. You can times it all by 7 if you wish, and you can write like this. It's not equal to the line above, but it does answer the question as well. So you might see it written like that, or you might see it written like this. They're both the case that you have a quadratic. All right. Similarly for question 8. So for question 8, so we're looking at this one here. That one there. 2x squared minus 3x minus 5. All right, so the sum alpha plus beta equals minus b, so which minus negative 3 is 3, over a, so 3 halves. Alpha beta, the sub product, is c on a, which is minus 5 on 2. Okay. Oh, I should write this. Actually, this is not alpha and beta, it's p and q. Let's use my eraser. That's why I put my thing up. So I made a mistake. Okay, let's use the terms they used. Okay, so p plus q, and then p times q. All right. Now, once again, okay, final quadratic equation with roots, p squared plus q and q squared plus p. Let's see what happens when we add these. All right. Now, new roots. P squared plus q and q squared plus p. All right, let's find the sum of those. P squared plus q squared plus p. Now somehow we have to, now I can bring in those two together to make that. It's not quite the same thing to say that. Okay, now the way I'm thinking about it, I actually got stuck on this when I tried it in class the first time, but I can kind of see it like this. You know what? No. There may be one more way to do this, but I think and I'm going to group up the P and the Q. Okay. Oh no, so it's still P plus Q, it's not P times Q. Maybe I'll notice that as well. Okay. All right, so plus P plus Q. Now we know that that can be expressed as that, so 3 halves. Well, what about this P squared and Q squared? Yeah. The way I'm going to do that is I'm actually going to complete the square by adding this in the middle, but then I have to also subtract as well. So this P plus Q is, I might as well just turn that into 3 halves now. And then I have this other section, which is, I have to do this because otherwise that's imbalanced. Okay, now why did I do that? Well, this first 3 terms I can then factorize to this P plus Q squared. See, now you've got something that you can bring into this. We still have the plus 3 halves there, and we have the minus 2. Now that's minus 3 on 2, something like that. P plus Q is 3 halves, so 3 halves squared plus 3 halves. Okay, minus 2 times minus 5 on 2 is 5. So now we've got 9 on 4 plus 3 halves plus 5. Oh boy. And that can be written as 6 on 4, which then I could, okay, so now we've got 15 on 4 plus 5 wholes. 5 wholes is 20 on 4, which can be written as 20 on 4 plus 15 is 35 on 4. Okay, that's the sum. Product. Okay. All right, so this might be a bit tricky, but we'll see how we go. We get a light on the subject. Yeah, it should help a bit. Okay, let's expand this and see what happens. P squared Q squared plus P cubed. Oh boy, plus Q cubed plus PQ. I don't like it. All right. Now these ones I can group up because that could be written as PQ squared plus P3 plus Q3 plus PQ. All right, that can be written as 5 on 2 squared plus all right, so we got square that 25 on 4 minus 5 on 4. Let's group that part up. 5 on 2 rather. Plus P cubed plus Q cubed. I don't know what to do with that. All right, but I can at least reduce this part down. 10 on 4, that's a 15 on 4. All right, now this is actually meant to be a pretty challenging question. I wouldn't expect to do this sort of thing in the SAT or exam, but yeah. We'll be going through, I could think of a way to do that, but not in the scope of what we taught in this chapter. I'm inclined to almost leave it at that rate. Because I can actually reduce it. There is a way to do it, but I'm just going to do it. Okay, there's a kind of an extension to completing the square where I can complete. All right. This is going to come, unless you've seen it before, it's a complete mystery why I'm doing this. I'm not exactly sure how else to do it. Okay. It's a bit like the perfect square rule, but it's for like P plus Q bracket to the power of 5. It's power of 3. You can try it yourself and see what happens. It does work. Now I have to undo that as well. So minus P squared is the binomial expansion of P plus Q cubed. And I'm going to factorize that in a minute. Well, let's get on with it. Oops, 15. So all this part then factorizes to P plus Q to the power of 3. Then we have minus 3. I'm actually going to take a P out of that one. It becomes PQ, which I know what to do with. And then I have minus 3Q PQ. Okay, so that I know what to do with. So I've got 15 on 4 plus. P plus Q. So this is, yeah, I don't expect a lot of people necessarily to completely get this one, but it's tricky. Minus 5 on 2, minus 3Q, minus 5 on 2. All right, so we've got these terms here. 15 on 4. Cube of that, cube of 3 is 27. So, hang on, is that negative? No, it's not. 15 on 4 plus 27 on 8. And if I expand this part, I'll now have plus 15 on 2 lots of P plus 15 on 2 lots of Q. Now, I've still got P's and Q's, but they're going to go away in a minute. And I'll show you why, because I'm going to group them up, and we basically have it. So that can be written as 30 on 8. 30 on 8 plus 27 on 8 is 57 on 8 plus 15 on 2. So I'm factorizing the last two terms, but taking out 15 on 2. PQ. There's my last P plus Q. So then I can substitute in, 3 on 2. And I'm going to put that over here. So we have 57 on 8 plus 15 on 2 times by 3 on 2. All right, so that will be 45 on 4, that part there, which can be 90 on 8. So finally, 19 on 8 plus 57 on 8 will be 147 on 8. Now, fingers crossed I didn't actually make an error there somewhere. If I've not made an error, then let's just go up here and I'll write out the final answer. Now, this is actually all quadratic, so we have to put an A on there. A x squared minus the sum. The sum was 35 on 4 x plus the product, which is 147 on 8, if I didn't make a mistake. Variations of that will just be if you times like this whole thing by 8 and just assume A absorbs that, then you might have x squared minus 70x plus 147. Assuming I didn't make a mistake. That's basically the method though anyway for question 8. And that's the last I want to really see about this stuff for a while, because it's just it's kind of like, it's nasty algebra for the sake of algebra. It's not, you're not learning anything necessarily that you haven't already got out of the quadratic formula. So let's move on to something different. So let's move on to the chapter 2E's. Let's go to those. So we're going now to page 49. Okay, so page 49. So question 4A and C. Is that right? A and C. Is C on the next part? No, it's not. Let's check the email again. There's no C, so I'll do A. I'll just do A, and then we'll move on. Okay, find the form of AX plus B. And let's just check if I've got the right chapter. Maybe it's the chapter's wrong. That's E. That is E, and I am doing E. Okay. All right, well, let's just do A. There's no C. Someone can ask me to do B another time if they want, if that was the intent. Okay. Find the form of that equation that cuts the x-axis at... Okay, so we got y equals ax squared plus bx plus c. Cuts the x-axis, passes the x-axis. All right, so we have x-intercept equals 3. It has another coordinate of 5, 12. All right, and axis of symmetry. x equals 2. Now, the idea of that, now if you've got like a quadratic, you have an axis of symmetry. Okay, so your axis of symmetry is that line there. Okay, and that's the line of x equals 2. Now you have a corner over here of 3. Now the idea of symmetry is whatever's to the right must be mirrored on the left. So if that's at 2 and that's at 3, then this must be, if that's 1 unit over, this must be 1 unit over, so that must be at 1. So we're also telling you we have, we also have x equals 1 as another, as another x-intercept. So put it there. All right, so we have 2 x-intercepts. So now, I don't think we've learned factorized forms. Yes, we have. Yeah, we did factorized forms in there. So let's write it out that way to start off with. Okay, so a x minus 3 and x minus 1. Okay, expand that out. A bracket. X squared minus 3 minus 1 is minus 4x plus 3. Okay. Now we can go and we'll just make that y for the time being. Okay, y equals that. Okay, now without expanding the a in there, we're just going to substitute this value here, 512. So 12 equals a 5 squared minus 4 times 5 plus 3. So 25 minus 20 plus 3, which would be 12 equals a. 25 minus 20 is 5 plus 3 is 8. Okay, so divide both sides by 8. A equals 12 over 8. Now they both have a common factor of 4, so that'll be 3 and that'll be 2. So A can be written as 3 halves. So thereby, y equals 3 halves. Now, if you then you have to expand that in there. So maybe I'll write it out in this form, because it's asking us for a particular form. So then I'll multiply this in here. So that's equal to 3 halves of x squared. 3 halves times 4 is 12 halves, which is minus 6. And then 3 halves times 3 is 9 halves. And I've written in the form that they want. So that was for A. Put that up there. Let's go back to our list. All right. So let's go to page 53. All right, 6, 7, and 8. Okay. So these are about intersections between lines and graphs. All right. So in the first case, we've got as we can see here. Now I might use this little product here because we got this. So consider this. So they've actually got a little application here that I can use. If you move this, so we'll place it about where they've got it in the picture on the screen, so like on here. All right, so at minus 3, you've got no solutions. So that's for a 6C. There's no solutions in this region. Then you come to a point, actually, that's where you get 1 solution, 2 solutions. But you find if you keep going, nope. Actually, no, you can't. There is not another set. Okay, unless, nope, not with that slope. So yeah, whereas the one for question 7, you can actually swing the slope around. You actually can look at it in 2 ways. So that's an interesting way to look at it. Okay, I might bring that up again in a minute, but let me just do the math. Okay, so with these problems, we've been equating. So this is from the unit with intersections between lines and quadratics. All right, so we say y equals x squared plus 4x minus 1, and we're going to equate that to that line. So we want to see the lines meet. Now we're going to bring everything across the other side. So on the left-hand side, subtract 2x plus 2x. and then we have minus 1 minus c equals 0. Okay. Now, whenever you've got a quadratic equation and you bring everything across and equate it to 0, the discriminant tells you the circumstances where you see 1, 2, or no solutions. Let's look at the discriminant. B squared minus 4ac. Okay, so b squared is, we got 2 squared minus 4 times 1 times, be careful, minus 1 minus c is actually what our c term is over here. Okay, 4. Okay, if I multiply that in, minus 4 times minus 1 is positive 4, and then that will be plus 4c. So 8 plus 4c. Now, discriminant, if it is equal to 0, let's see what happens. Equal to 0, that will be solving for tangent. That will actually be solving for b in this question. But it's actually important we kind of establish where that is. All right, so move that across. 4c equals minus 8. C equals minus 2. All right, so that's the value of a c where you get a tangent. So that means there's only one solution. If you have a larger value of c than that, so if you have minus 1, you end up with positive values. So for c greater than -2, that will be the solutions for A. You can check that by substituting a value. So if I put in like 0, I would get a positive value here. So that if it's greater than 0, then that means there's 2 solutions. That's like kind of 2. And if c is less than -2, that's a c value, that would be no real solutions. Because if you substitute a value like that, and if you put -3, for example, you have 8 take 12, which would be negative and thereby no solution in real numbers. And that's the case for C. Does not meet the curve. Let's see if that's about accurate for what we see in the picture. Okay, so we put the slider at 2. Yeah, when the y-intercept is 2 for the line, yes, there's only one solution. That's there. If it's more negative than that, it does not meet it at all. If it is larger in c value, there we go up. You see, you get as soon as you get 2, as soon as you go above that, you get 2 solutions, and then there's 2 solutions for all values, and so on and so forth. Okay, so that was question 7. All right, one more, question 8. A similar kind of theme. All right, but this one, question 8. We're now going to equate this quadratic here. 2x minus x, take 2 and equate that to, no, it's 6. I haven't done 7. Let's get ahead of myself. All right. So we've got question 7. Question 7. All right, so we've got minus x minus 3 plus 3x minus 6 equals mx minus 2. So what do I get when I equate that? Let's have a look at the picture and the thing here. So I'm varying the slope of the line. So let's see what happens then. Okay, so if I go up, that makes the slope steeper. And you can see as the line's getting closer and closer, it's not meeting until we get to 6, 7. And then if I go above 7, I get 2 solutions. Well, what if I swung it right around the other way? 0. Okay, ooh, minus 1. And then there's other solutions. There's double solutions. Okay, that's interesting. So let's see what how that pops up. Well, okay. Let's So it's really easier if you solve for part B first, because that's when it's equal. And then you kind of work out from there with your sign with the signs and work out where to go from there. Okay, so bring everything across to one side. Plus 3 minus m loss of x, take 4 equals 0. It would just be easy if you times everything by minus 1. Just be careful. X squared plus, okay, that would actually be, if I times this by minus 1, it would be m take 3 instead of 3 take m. 4 equals 0. So now there's less negatives to deal with. Yay. Look at this. Look at the discriminant again. B squared, which would be m take 3 squared minus 4 times a times c. Okay, let's see what happens. Now this is already kind of in a factorized form, so I can solve this without having to expand it. It's in sort of completing the square kind of territory. Minus 16 equals 0. So I'm solving for part B first because it's easier that way. I mean, you basically end up doing the same thing. You have to solve for when it's greater than 0, and you can move things around just to solve for it. Yeah, if you want to, I'll just for the sake of it, let's just show you what you do if you have to do part A first. If you do that in that order. Basically, part A, just change all these equal signs to greater than signs. Okay, let's do it that way. All you have to do is just be careful. If you times by or divide by negatives, you have to switch the sign of the inequality. All right. So then, okay, move that. If you add, that's fine. Add 16. Which I think this is why I did equals. So I was confused to say the results of whether I have to plus or minus that. What effect that would have when I did this question in class. If I take the square root, it's plus or minus 4. Yeah, that's why I might even just go back to 0. Sorry, changed my mind. Let's just do equal signs, and then we just do some sign diagrams and just think about it from there. Let's just do part B first. It's just easier. Okay, so then there's just plus or minus 4, and then move your m across m. 3 plus or minus 4. So these are the solutions actually, because I've gone back to B. I changed my mind. With 7 and minus 1, those are the ones we saw before. Okay, but what does that mean? That means the ones where if you swing this orange line around, so the slope is higher or smaller. When it's at 7, it touches once. If it's at minus 1, it touches once. Outside that, okay, so maybe we just draw a sign diagram for m, and we show you what. So we're doing a sign diagram of the discriminant. So we've got 2 zeros of the discriminant, which are minus 1 and 7. So let's talk about the discriminant in terms of a sign diagram. Okay, if you have numbers between that, so if I picked in discriminant, if I picked in 0. So if I substitute 0 into the discriminant, like in here, 0, 0, no, hang on, it's not discriminant, that's a discriminant. All right, it's values of m. If m equals 0, I've got 3 squared, that's 9, take 16, that's negative. Yeah, there's no solutions in that one, and the outside of these two, there'll be positives. You can substitute numbers to check, but I'm pretty certain that's correct. Because the discriminant is a quadratic in its own right. Excuse me. So what does that mean? Okay, for part A, that means m is less than minus 1 and or greater than 7. For part B, m is equal to 1 or 7. And for part C, m falls between -1 and 7. It's easy just to think of it that way. Okay, very last question. Now it's time for question 8. Let's move on with that one. Show that any linear function passing through that will meet the curve of that twice. All right. Well, let's talk about a linear line. So let's consider constructing something. So a linear line takes the form of y equals mx plus c. Now we actually happen to have the y-intercept of that. So thereby y equals mx plus 3. So it's actually very similar to the last question, but I imagine because this is a positive, this is actually a linear line which is drawn above the x-axis with a concave up quadratic, that this will always have discriminants that are positive. Let's prove that's the case. Let's equate the lines with the quadratic. Okay, so x minus 2x minus x minus 2 equals mx plus 3. Okay, let's group everything up. X squared plus minus m minus 1 minus 5 equals 0. Sorry, there's an x in there as well. I'm going to times this all by minus 1 because there's too many negatives for my liking. 2x, okay, and then there'll be minus 1 in there, so that'll be m plus 1 lots of x plus 5 equals 0. Alright, so now, okay, well, let's look at the discriminant. This would tell us how many solutions we have. Alright, b squared minus 4ac equals m plus 1 squared minus 4 times negative 2 times 5 okay. What if I made a mistake because it's not actually doing what I think it should be doing? Oh, that was minus 5, that's plus 5. Even if I do that, all right. I think I've got a mistake in here somewhere. Have I done something? Have I copied this down wrong? I'm just noticing that I've got this will all be positive, so if I equated it to 0, or if I made, yeah, I'm just going to have trouble doing the square root because I'll be negative on the other side. I imagine I've made a mistake here, I just have to spot it. Okay. X equals 0, y equals 3, that's correct. Mx plus c, 2x squared minus x minus 2. Bring that across. Show the any linear function passing through P0, 3. Where's the curve that twice? Trying to find the mistake I've made, but it doesn't look like this is going to actually yield the solution I want. Because if I move that across, so that's 8, 10 plus 10 plus 20. I think I've stumped on this one. It's not working. Not doing what it's telling me it should do. As I move that across, I have a negative on the other side. If I take the square root, I've got no real solutions. There's a mistake in there somewhere. I don't know what it is. Minus 4. B squared minus 4ac. 8. 2. Okay. I do not believe a solution I'm done. I think there might be a mistake there if I don't see it. A quick look at the solutions, but I don't think they're going to telling us that we have to do it for all cases. The only thing I can think of is if I graphed it, is there something wrong with that graph? Y equals x squared minus x minus 2. Sorry, there's a 2 in front of that. No, it looks about right. Anything passing through here, any line that passes through that point should cut it twice. It makes sense to me. I can't make the maths show that though. Doesn't matter if I bring it the other way either. Oh boy. Stumped. It's either way. If I do it from that equation, either way I get one of the negatives and b squared minus 4ac. No, I'm not sure what to do about that. Can't spot my mistake. Might have to leave that one and see if someone else can possibly pick up the slack on that one. But maybe have a quick look back at the book and see if I've got something wrong. But I don't think so, because it's very similar to the previous question. I just can't get it to work. Alright, let's have a quick look back. So, round 2F. Bit embarrassing. Oopsies. So 2F. Here, in straight line through that. Yeah, well, that's exactly what I did. In straight line through 0, 3, we have an equation in the form of y equals mx plus 3. So I got that, I got y equals mx plus c, I equated it to this, I triple checked that this, I've written that down right. I bring that together, subtract mx on both sides, subtract 3 on both sides. So it's 2x squared minus m minus 1 loss of x minus 5. That should be, it doesn't matter what you pick, it's if you do that form or that form, you get exactly the same thing as far as the 20. No, I'm stumped on this. There's something going wrong here. I can't see it. Okay, we're going to leave that one there. So if anyone actually does come up with a better solution and can see where my mistake is, you're welcome to get the glory, get the gloating in. So I'm going to leave the video there. All right, catch you later.